Following on from the previous video, we mapped a quadratic on top of a cosine graph by ensuring that the first derivative of this matches up with the first derivative of this, and by ensuring that the second derivative of this matches up with the second derivative of this. So here we've only taken up to x squared. We could take it up to x to the power of 100, or we could take it up to x to the power of infinity, if that makes sense. We could so here we've only taken up to x squared. We've only taken up to x squared. We could look at the cubic, or we could look at x up to x to the power 4 or x to the power 5. In fact, we can actually take it all the way to infinity. But each time we do it, make sure that so here we could take it up to x to the power of 100 if we wanted to. But each time you do it, you have to ensure that the first derivative matches up with the first derivative. Second derivative matches up with the second. The third derivative matches up with the third derivative. Fourth derivative matches up with the fourth derivative. Make sure, for some strange reason, if you ensure that all the derivatives matches up, then for some reason this blue line here will eventually map on top of the cosine graph for some strange reason. But when you come to do this for a general case, make sure that you can differentiate this n number of times. So, for example, you can keep on differentiating this. If you look at e to the power of x, you can keep on differentiating e to the power of x n times. So differentiate that will give you e to the power of x. Differentiate it, e to the power of x, and so on. You can do it n times. You can do it in an infinite number of times. Another one is sine. You can keep on differentiating sine many times, or x to the power of -1. You can keep on differentiating this to an infinite number of times. So let me give you an example. So here we've only considered looking at a quadratic. So now let's try and take it up to x to the power of x to the power of 5. So our normal routine would be to ensure that the first derivative matches up, the second derivative matches up, third derivative matches up, and so on. So if you start out with our function here, our job here is to seek these coefficients here. And then the thing is, if we take this all the way to infinity, this function will map on top of the cosine graph. But let me just illustrate up to x to the power of 5. So if you differentiate this, this thing here disappears. So the first term will be a to the power of 1. Differentiate this. So the 2 will come down here. That will give you 2a sub 2, and then you've got your x here. Differentiate this. That will give you 3x squared, and so on. So if you differentiate this whole thing here, it will then give you this. So the first derivative is this. The second derivative will be this. Third derivative will be this. Fourth derivative will be this, and so on. Notice that this here is really 5 factorial. This here is 4 factorial, and so on. Just have that at the back of your mind. We're going to make use of it in the future. So here, fifth derivative is really 5 factorial. This is 5 factorial. Okay, so hang on. So our job here is to seek. A function so that will map on top of the cosine graph. So really, we are seeking these coefficients here. Okay, and by the way, you can rewrite this in summation form. You could rewrite this in summation form all the way to infinity. But we will leave that for another time. So we are trying to seek a function here that will map on top of the cosine graph. So we start out with our cosine graph. Differentiate it will then give us this. Differentiate it will then give us this. Differentiate it again, it will give us this, and so on. We want to ensure that the first derivative matches up with the first derivative. So when x equals 0, so if you put x equals 0 into here, x equals 0. So sine would be 0. So minus 0 will be 0. So the first derivative at x equals 0 will be, remember the reason why it's x equals 0 is because we are starting from this bit here and then expand outwards. Okay, so x equals 0. So hang on, going back to here. Bear with me. So we want to ensure that everything matches up. So when x equals 0, this thing here equals 0. So we want to ensure that this thing here matches up with this thing here. So we want to set this to be 0. So when x equals 0, you can see that if you put 0 into here, this whole thing here disappears. Put 0 into this x here, the whole thing disappears, the whole thing disappears, the whole thing disappears. So a1 here equals 0. Okay, so this a1 here equals 0. And also we need to ensure that, well, I said that ensure all the derivative matches up. Make sure all the derivatives matches up. We've got to make sure that the original function matches up as well. So when x equals 0, this thing here will be 1. So we want to make sure the original matches up as well. So 1, and then when x equals 0, put 0 into here, this thing disappears, put 0 into here, 0 squared will be 0 times this thing will disappear, disappear. So a1 equals, a0 equals 1. So what we've got so far is a0 is 1, this thing here is 0, we just worked it out earlier. And now we need to make sure the second derivative matches up. Now we need to make sure that this matches up with this. So when x equals 0, the second derivative will be negative 1. So because cosine of 0 will be 1, and then you've got your negative here. So the second derivative will be minus 1. So this whole thing here will be minus 1. So at x equals 0, put 0 into here. This would disappear. This would disappear. This would disappear. This would disappear. So a2 is actually minus 1 divided by 2. So that would be minus a half. So a2 here would be minus a half. And then the third derivative, well, put 0 into the third derivative. This would be 0. So set this to be 0. So set this to be 0. And then at x equals 0, this whole thing here, well, when you put 0 into this x here, it disappears. Put 0 into here, this whole thing here disappears. So a2 equals this thing here. So it's really 3 factorial. So 0 divided by 3 factorial, that would be 0. So a3 is 0. So a3 here is 0. So hang on, let me clear this up. So we are on the fourth derivative now. So hang on. So let me clear this up. So with the fourth derivative, we need to make sure that the fourth derivative matches up with the fourth derivative over here. So when x equals 0, you can see the fourth derivative equals 1. So set this to be 1. So hang on, let me clear this up again. So set this to be 1. So set this to be 1, because the derivative here at the fourth derivative here is 1. So set this to be 1. At x equals 0, this thing here will disappear because x is 0 here. So a4 is really 1 divided by 4 factorial. So a4, this a4 here, is really 1 divided by 4 factorial. And if you continue the process here, x equals 0, put it into here, this will be 0. So this thing here will be 0. So a5 will be 0. So a5 will be 0. So look at the coefficients here. This is 1. So this disappears, and then this is a negative a half, and then this disappears. This disappears. This is 1 over 4 factorial. So our function here is this. Okay, so if you get a graph plotter and plot it, plot this, get a graph plotter and plot this. You see, our quadratic approximation gave us this. Up to x to the power 4. Well, we took it up to x to the power 5, but the coefficient here is 0, so we ignore that. So it really boils down to this. Well, if you get a graph plotter and plot this, it will give you a better approximation to the cosine graph. You see, our quadratic gave us this, which was okay around this region, but then by you doing this, it's good up to here. It's good up to around here. So it will look like this. But the thing is, you can continue the process. You can continue the process and then take it up to x to the power of 8. So taking up to x to the power of 8 will give you this. You see, up to x to the power of 4 gave us x to the power of 4 gave us up to, it's good up to around here. It's good up to around here. But then taking up to x to the power of 8 is good up to around here. So you can see that as you continue the process up to x to the power of infinity, it gets better and better and better. In fact, if you take it up to infinity, it will map. This thing here will map on top of the cosine graph. But remember, each time you do it, you have to ensure that all the derivatives matches up. Okay.